Very good. Ladies and gentlemen, our last presentation of this year's lecture series on sustainability in computer science. And it is a premiere for having Georg Fuchsbauer in this lecture series about space-efficient blockchains. Just today I read in the newspaper that Bitpanda got some EU-wide cryptocurrency something. Of course, blockchains is not only cryptocurrencies, but I always have it together in my mind. Georg is really an international renowned researcher in this area of cryptography. Not symmetric cryptography in particular, when I understand correctly. And Georg, it's great to have you here, and it's your floor.
Thank you. Thanks a lot for the introduction. Can you see my mouse pointer on the slides?
Yes.
Okay,
yeah,
good.
Yeah. Also, Marco is here. Great. And Marco can see the mouse pointer.
Good. Okay. So for the sake of this talk, blockchains will mean cryptocurrencies. And I will talk about space-efficient blockchains/cryptocurrencies are the systems that prevent or that avoid having to store this huge amount of data like Bitcoin and Ethereum do. Okay, since we talk about blockchains, let's start with Bitcoin. So Bitcoin, what is it? It's a digital currency, arguably the most successful digital currency ever created. And the novel thing it introduced was that it's decentralized. So there's no central bank like in classical currency systems that emits coins, but everything is decentralized. And it had hard-coded inflation, which is not relevant for this talk, but which arguably contributed to Bitcoin's success in the beginning because Bitcoins were scarce. And it's pseudonymous, which arguably contributed to its bad reputation, at least for a long time. Now there's more anonymous cryptocurrencies taking on that role. Okay, how does Bitcoin achieve that? It maintains a public history of all transactions that ever happened. So everything is public. Everything can be publicly verified by everyone, and that guarantees consistency. And then the way different users agree on their view of the system, Bitcoin uses a distributed consensus mechanism, which also in this talk is not the most relevant aspect. Okay, so let's start with a public ledger. So arguably the simplest currency system you could imagine is if you have an authority that everyone trusts, then you don't care about privacy, then the authority could just every so often publish a snapshot of everyone's account balance. So if Alice now owns 1 unit and she wants to transfer it to Bob, she contacts the authority and the authority publishes a new ledger where Bob now owns this 1 unit. Okay, that's not exactly how Bitcoin does it because Bitcoin doesn't store the account balances, but it stores all transactions that ever happened, which is basically the same because if you follow all the transactions, then you can compute how much everyone owns. So now assume that Alice at some point got this coin from Charlie. She can now transfer it further to Bob by referencing this her transaction where she got the money. And that's how Bitcoin spends previous transactions. So in Bitcoin, there's no notion of account. There's only transactions. Now, the question is, of course, if you have this public authority, Alice can just go there and identify herself, but that's not how Bitcoin works. So how do people identify what makes you own a coin? So that's what we use digital signatures for, where Alice can create a key pair consisting of a private signing key, a secret key, and a public key. And using her signing key, she can sign documents. That gives her a signature, which can then be verified using the public key. And that's something that all of us use every day because it's used, for example, in the HTTPS protocol. Okay, for simplicity here, I associate a public key with a coin. And so if you own the secret key that goes with the public key that represents the coin, then you can spend that coin. How do you do that? Assume Alice owns a coin pKa and it's in the ledger, and she wants to give that coin to Bob. Then Bob creates a new public key where in Bitcoin this would correspond to addresses, but yeah, I'll just assume the public keys are there in the clear and not hashed like it's done in Bitcoin. And now Alice transfers her coin to Bob by signing a transaction that says what was owned by pKa is now owned by pKb, and I sign this, and so I allow this transaction. This is added to the ledger. Now, how does Bitcoin address this notorious problem called double spending? Namely, what prevents Alice from sending her coin to Bob and then sending it to Charlie as well? That would be bad for a currency system. That's something that for physical coins is not a problem, right? Because physical coins, they're hard to create. Digital coins maybe as well, but then digital coins are easy to copy. But if you have a public ledger and everything is public, then that's actually easy to solve, because you just say that the ledger only accepts a new transaction of this form here if there exists a transaction that gave pKa the money, right? And the money has not been spent yet. There has not been a transaction yet that from pKa moved the money somewhere else. So if everything is public, you could just enforce that every transaction is only spent once. Okay, the question now is, how did Bitcoin eliminate this hypothetical central authority? How did it decentralize everything? How did it make sure that the validity of transaction was checked and that every now and then new transactions were published? That was the concept of the blockchain, where a block is now just a set of transactions, and in Bitcoin every 10 minutes there's a new block, so new transactions are published, and then these blocks are linked together by hashes. But again, this is not the topic of this talk. It leads to questions of how can you incentivize miners to publish these blocks. The way it's done is that every block creates new currency in the system. But then how is a consensus reached between the miners? How do you guarantee that no one can subvert the system? That's actually all been talked about in an earlier talk in this lecture series by Krzysztof Pieczak on sustainable blockchains. So you might want to watch that if you're curious about these aspects. Okay, all I'm saying now is that it is one of these components that work together to make Bitcoin secure. So we said if we had a trusted ledger, then we could use it to make a payment system, right? If we have a payment system, then we can incentivize miners by giving them fresh money for every block. And if we have these miners that run these consensus protocols, then from that we get a trusted ledger. So you see that you have these self-enforcing cycle of concepts that Bitcoin put together in a very clever way. Okay, so let's look at transactions in a little bit more detail, because it will be relevant for this aspect of this ever-growing blockchain and how to avoid it. So for now, we said Alice has 6 Bitcoins. She wants to give it to Bob. What if Alice never received a 6 Bitcoin coin, but she actually received 2 Bitcoins and 2 Bitcoins and 3 Bitcoins in the past? Then luckily what Bitcoin allows you to do is have several inputs to one transaction. And in this case, Alice would probably not make this transaction because that sums up to 7, and that's like $100,000 difference. So what she can do, luckily, she can also make several outputs in this transaction and then just send 1 Bitcoin back to her own address to a public key that she owns, and let that be the change. What actually happens is that the output sum will not be exactly the input sum, because typically the outputs will be less, because that are fees that you give to the miner to incentivize them to even take your transaction and putting it into a block. Because if they don't get anything for your transaction, then they would probably not do it. Good, for this talk, we'll just ignore fees, but they're helpful for this transaction to end up in a block. And so the miners collect transactions, publish this new block, which represents the new epoch of the system. And now if Bob, remember Bob got these 6 Bitcoins here, if Bob wants to spend these 6 Bitcoins, he can create a new transaction, say spend 2 to Charlie and 4 to Dave. And this new transaction now references the old transaction. So he says, this is the output that I'm spending as input in this new transaction. And he broadcasts this transaction, it's picked up by the miners, it's put into a block and is chained to this blockchain. Okay, so every input of a transaction spends an output of a previous transaction, right? So these transactions as well, they refer to some transaction outputs in the past. So now you might wonder, where does the money come from? And I told you the money is created to incentivize miners. So it's in every block, there's just currently it's 3 1/8 of Bitcoin that's freshly generated. And that's now new money, and that can also be spent. So a transaction input could also point to this kind of new fresh money created in a block, and that's called a coin-based transaction. So if you look at all the transaction outputs, some of them will be spent by new transactions, and the ones that have not been spent yet are the unspent transaction outputs, or UTXOs in Bitcoin lingo, and they represent all the money that exists in the system because it's the transactions or the outputs of transactions that can still be spent. Okay, what does it mean to own an output? As I said, it's, the secret key associated to a public key that's associated to that output. So every transaction output has a public key associated to it. And if you know the secret key, only then can you spend it. Why? Because when you spend it, when you refer to it in a new transaction, you actually have to give a signature under that public key on this new transaction. And so since signatures are unforgeable, and if you take care of your secret key, then no one else can spend your output. So we have one of the security properties that the signatures guarantee that no one can steal someone else's coin. We have another property that's kind of obvious for now, but we'll come back to it later, which is that a transaction cannot just create new money, because for a transaction to be valid, we require that the sum of the outputs is less or equal to the sum of the inputs. So no illegal creation of money. So keep that in mind, because we'll come back to it. So I hope I'm still on. Two drawbacks of this system is that all the transactions are public. So it's actually kind of a weak notion of anonymity, because if for some reason, network analysis or whatever, who made this transaction here or who owns the transaction output, then you see exactly when this transaction will be spent. So you can analyze the transaction graph, and there's even companies that do that for business. Again, anonymity, not the topic of this talk. What's more worrying from a sustainability aspect is that all this data must be kept forever. Because if you want to verify this lower transaction here, you need to verify the signature, you need to check whether that corresponds to the public key, you need to check whether that transaction was legitimate, and so on, right? And so that's why this blockchain will keep all the material forever so that it is publicly verifiable. And so that's kind of a bad scalability. If we look at the numbers, then the blockchain size of Bitcoin is now over 600 gigabytes, and it's linearly increasing because every block adds at most 1 megabyte of new data. There's other systems where it's worse, like Ethereum. There, the blockchain is double as big. And the problem is that if you want to join the protocol, if you want to become what's called a full node and you want to mine or contribute to the security of the protocol, you need to download all historic data, so all these 600 gigabytes, verify every signature, because only then can you be sure that you have an authentic copy of the blockchain. Obviously, afterwards, if you want to maintain, be a full node, all you need to remember are the unspent transaction outputs, because that's kind of what you need if a new transaction comes to check whether that transaction is valid. And that's a lot less in size. So that's less than 10 gigabytes. And as you can see here, this is also something that can decrease over time. If more outputs are spent than created, then that set can also shrink. But if you join the system and someone gives you this UTXO set, then you cannot be sure whether it's correct, because you cannot verify anything. So that's why we need this full 600 gigabyte of data. The question is, can we do better? Can we have a system where we can only store what's needed to check whether new transactions are legitimate? So all basically the information about the money that exists in the system, so this UTXO set, and still have full verifiability of the system despite not having the full transaction history. And that's basically, in other words, what we would like is that if we have the situation, we have some transaction output here, it's spent, and then all the outputs of this transaction are spent again. We'd like to forget about these spent transactions and basically point back to where the money came from. Obviously, in Bitcoin, that's not possible, because even like if you look at the signature, it has to be verified under this public key here, so you need to remember it. So this notion is like the technical term people use is called cut-through, because you can somehow get rid of the things that discard old data that's not needed anymore. And that's exactly what the first approach I wanted to talk about achieves. It's called Mimblewimble, and it's a cryptocurrency scheme, and as has proved good practice for cryptocurrency protocols, it was proposed by an anonymous or pseudonymous author. In this case, he went by the name of Tom Elvis Jedusor, which is the French name of this Harry Potter character called, I think, Voldemort in English. And the scheme was basically proposed by a very short, very informal text file. Used a lot of ideas that had been around, by most of them from Gregory Maxwell, and it was then further developed by Andrew Poelstra. And I think the main motivation was privacy. So it's a cryptocurrency that achieves a lot better privacy than Bitcoin. We'll see how it does so. So it hides the amounts that are transferred, and it kind of blurs the transaction graph, so you don't see where the money moves. And if you look at the document, that also seemed to be the main motivation of the author, because he talks about companies whose business model it is to monitor and control the lower classes. That's kind of the privacy aspect. What I found a lot more fascinating about this proposal is the scalability aspect, because it allows us to forget about spent transactions and keep the data more compact. So we've now, there was only this informal proposal. It seemed very unlikely that the whole thing would be secure. So together with Michele Oru and Yannick Sorin, we analyzed the scheme, and we gave a formal security proof that it was secure. Good. So let me talk about how this system works. Tried to not get too technical. Let's see if I manage to. So the first anonymity that was already observed in Bitcoin was that transactions are basically atomic, right? So if you have inputs and output, there's no notion of which input goes to which output. So this first output could be the result of the first and the third transaction, or the second transaction. There's no such notion. So what people thought, if you want to kind of hide who pays whom, a concept called coin join, which in Bitcoin only works interactively. And the idea is that a lot of people come together and like have their transaction where they want to pay someone with coins they own. They put everything into one big transaction, then everyone signs, and no one knows who paid who. The problem is that this in Bitcoin only works in an interactive way because everyone has to sign the whole transaction. So you can't just take two transactions that exist and then merge them together and kind of mix them a posteriori. Okay, that's actually one of the things that Mimblewimble achieves, and we'll see how. The second anonymity notion is about hiding amounts. So can you, instead of having these amounts of inputs and outputs in the clear, can you somehow encrypt them or hide them? That's a concept that has also been around for a while, called confidential transactions, and it's not compatible with Bitcoin. It would like need a major change to the protocol, but it's used by other cryptocurrencies such as Monero, which is kind of, I guess, the biggest so-called privacy coin. Here, the issue is that if you hide the amounts, you don't know anymore whether the transaction is balanced, right? You don't know whether this is a transaction that suddenly the output is a lot more than what went in, which would be bad for a currency system. So let me show you how this is actually done, how you can hide the amounts, but at the same time make sure that the amounts on the output side are the same, their sum is the same as the amount on the input side. So this is done by using a cryptographic concept called a commitment, which is often described as a digital envelope. So we have Alice that can commit to a value V. So think of, she takes this value, puts it into an envelope, puts it on the table, so Bob cannot see what's the value that's inside. Or in crypto terms, the commitment is hiding, but later she can open this envelope and show the value, and she can't change it anymore, right? Because the value is in the envelope and Bob observes everything. So that's what's called binding. There's only one way that Alice can open this envelope. So here comes the one technical slide. How do you realize this using cryptography? You use what's called a discrete log hard group, which is, if you've ever heard the word elliptic curve cryptography, that's what it's about. It's structures in which you can compute, and there's a problem that's hard. So you have some set G and some operation plus, and you have a generator. Think of it's like your unit element. And if I take this generator and add it to itself a random number of times, so compute x times g, then it's hard to find x. That's the discrete logarithm problem. So using a group where this is hard, here's how the so-called Pedersen commitment scheme works. So suppose we have two of these group elements, two generators G and H. Then what Alice does when she wants to commit to a value V, so this digital analog of putting it in the envelope, she picks a random value R, and she computes the commitment as her committed value V times the element H plus R times G. And you can show that this completely hides the value V. And at the same time, as long as the discrete logarithm is hard, Alice can only open this in one way. There's only one way of revealing some V and then a value R, so that this results in this commitment here. Okay, so the one property that's used for this confidential transactions is that this is actually homomorphic. So what does that mean? It means that if you take two commitments, so a commitment to value 1 and a commitment to value 2, if you just plug in the definition and rearrange, then you get a commitment to the sum of the values using the sum of the randomness. So here's an example. If I have a commitment to 1 using randomness 5, a commitment to 1 using randomness 10, I add them, and then I subtract the commitment 2 using randomness 15, then everything cancels out, and I get 0. And maybe this now already gives you an idea of how I can show that stuff is balanced, although you don't see the committed values. So here's how confidential transactions work. instead of having clear amounts that are spent and created by a transaction, everything is committed. But to check whether the commitment is well balanced, what you do is you sum all the output commitments, you subtract all the input commitments, and that should give you 0. And if you look at like just the definition, since the sum of the outputs minus the sum of the inputs is the commitment to the sum of the output values minus the sum of the input values, if it's well balanced, that's 0. And if you arrange the randomness correctly, that will also give you 0. So that's confidential transactions. So here was kind of the what existed when this Jedusor guy appears and says, I take these ideas a lot further, and here's how I define this Mimblewimble system. So the problem with confidential transaction is that, yes, it gives you privacy, but you still have these signatures in here, right? And the signatures were the reason why you have to keep all the transactions, because you have to verify all the data. So you can't do this non-interactive coin join. You can't take transactions and put them together and they look like a new transaction. You can't erase any data. You need these signatures. So enter Jedusor, who says, let's get rid of the signatures. If there's no more signatures, we also don't need the public keys. Now you might ask, well, then what makes me own a coin? If there's no secret information associated to an output, everyone might spend it. And he says, what's the secret key that goes with a coin is this randomness that you used when you hit the amount. So this, when you computed this commitment to the amount, this randomness will act as the secret key. Now, at first sight, there's a problem because the sender knows the sum of the output randomnesses, because I told you that you have to somehow make sure that not only in this equation only the values, but also the randomnesses balance out. And in particular, if you had a transaction using this idea where there's only one input and one output, then by using Pedersen commitments, it would actually be the same coin. And so it means that the new coin has the same secret key as the old coin, and so whoever owned it before still owns it, and you didn't really get a new coin. So what Jedusor says, well, let just everyone pick independent randomness. So if I create the coin, I pick a new randomness, and so I'm the only one who knows the randomness that is associated to this coin. Obviously, if you do that, then if you look at this equation, the randomness will not cancel out. What will still cancel out, if it's well balanced, are the values, right? Because the input values should be the same as the output values, so that should cancel out. So what this equation here becomes is that it's equivalent to 0 times h, so the values cancel out, plus some x times g, where x is just this sum difference of sums of randomnesses. Okay, so then he says, well, if you want to make sure that this transaction is well balanced, then prove to me that this sum of the outputs minus the sum of the inputs is a commitment to 0, because that means that no money was created. So he adds to this transaction a signature under this public key. So this is kind of technical why it's a signature and not a proof, but it's basically a Schnorr signature, which is a proof of its secret key. Anyway, long story short, this signature guarantees that this value here is really a commitment to 0. And so we've shown that the transaction is balanced. Okay. But the question is, of course, he's gotten rid of all the signatures, so everything that kind of authenticates a payment. So he claims that's still secure. And that's kind of how I felt when I read it. And so to the drawing board, see if that's actually true, that because only I know this randomness used for committing when I created the coin, I'm the only one who can spend it. And after long analysis and complicated proofs, we could actually show that under the assumption that the discrete logarithm problem is hard, that's actually the case. So no one can steal your coin. although there's only this, this one signature for the whole transaction. Okay, so if you've zoomed out, that's normal. I know it was a bit technical, but here's the kind of the effect that all of this has. So if you look at the Mimblewimble transaction, we have committed hidden inputs and outputs, and a transaction is valid if the sum of the outputs minus the sum of the inputs is this, this element X here, and we have the signature that's valid under the public key X. So this signature guarantees that this expression here is well balanced, and magically at the same time it guarantees that only the owners of these coins could have contributed to making this transaction. And if you have a coin in the system, no one can steal it if you keep your secret key safe. Okay, now what I find more like, here come the fascinating consequences of this simplification. So the first one is, if I have two transactions, so I have transaction 1 and transaction 2, they're both valid, then I can just glue them together. So if I take the two equations that give me well-balancedness and I sum them up, then I will get that the sum of the overall outputs minus the sum of the overall inputs will be the sum of these X values, will be X1 plus X2. So that will be my new equation. And I have just put these transactions together. And you can actually add some more techniques, I won't go into it, to re-randomize things so that this transaction now really hides which inputs come from which transaction. So you really took two transactions, you put them together in a way that you don't know anymore how the money moved originally. But I think the more fascinating consequence is the following. Suppose that the first transaction created some output, the one in blue here, that was then spent by the second transaction, right? That's exactly this idea of cut through. If something has been spent, can I get rid of it? And so now I claim what we can do without hurting the validity of the transaction, we can just, I'll get to that. We can just, so assume these two are the same, we can just get rid of them. Why? Because if you look at the validity equation here, then this element appears in the list of outputs and in the list of inputs, so they cancel each other out. So if I remove them from both, it will still remain valid, and I've just removed what was spent, and the transaction is still verifiable and valid. Okay, what I skipped was that you can even do better, and if you use what's called an aggregate signature scheme, you could even compress these signatures into one signature and thereby remove additional data. Okay, so we've actually achieved exactly that. If something has been spent, you can just remove it, and since the signatures are not specific to every transaction, but somehow global, and by this magic of canceling things out, you will still maintain verifiability. So if you play this game further and you take all the transactions in your blockchain and you all merge them together, then what will happen is that since every transaction that was spent some other previous money, all that will be left are the coin-based transaction, and all the outputs that will be left are the unspent transactions. So the blockchain in Mimblewimble is just one gigantic transaction where all the outputs are all the outputs that haven't been spent yet, because the ones that were spent were removed using this cut through, and all the inputs are the coin-based transactions, because all the other inputs would correspond to spent outputs, and so they were removed. So that's kind of the system view. So it's all nice academic theory. Who would ever use something like this? Well, in blockchains, every new thing is immediately used, because that's kind of can be your selling point for a new cryptocurrency. So it's implemented by several cryptocurrencies since 2019. Well, not Bitcoin, not Ethereum, but if you go further down the list, actually quite a bit further, you find some coins that are worth a few $1 billion. that are based on this Mimblewimble protocol. So a drawback of the protocol was that the transaction, since there was randomness, there was like secret keys of the sender and the receiver, had to be made in an interactive way. So the sender and the receiver had to talk together, and that's not what you would usually like. Like in Bitcoin, if you have someone's address, you can just send money without interacting to that person. And there were proposals to make this Mimblewimble system non-interactive by David Burkett and Gary Yu. And so we've analyzed it and found a few flaws and fixed it, and also gave a proof for this extension to be secure. And this was then also implemented since then by a coin called Mimblewimble coin. And see here, we're already approaching the top of the list. So that's already more substantial currencies. But then in 2022, the protocol was implemented by Litecoin as so-called Mimblewimble extension blocks. And for those who've never heard of Litecoin, Litecoin was the second cryptocurrency after Bitcoin, and it's still among the top 20 Bitcoins. So it has made some real-world impact. Good, that's all for Mimblewimble. Very briefly and basically just by pictures, I'll show you how you can do even crazier things and define a constant size blockchain using this CODA protocol that now was rebranded as Mina or Mina, I don't know how they pronounce it, where, remember in Bitcoin, we had the 600 gigabytes that would ever grow and grow and grow. Then I told you can use Mimblewimble, that makes everything a lot smaller, but it would still grow. And so here's a proposal about a blockchain that's 22 kilobytes big, and it will stay like that forever. How can you do this? So let's go back to our initial ledger-based system, where we have these snapshots of the system, and you can check whether a new snapshot was legitimately obtained from the previous one, like here, for example, where Alice's balance decreases, because there's a signature by Alice that says, yes, I spent this money to Bob. So you can always verify whether a new system view is correctly derived from the old one. So can we compress this? Yes, that's actually what Bitcoin does as well. You can do what's called a Merkle hash of a block, which you can just view as like a fingerprint of a block. It's 256 bits that represents the block. And there's it's a very clever way of hashing things together so that you can easily show that some information is contained in this hash value. Of course, you can't just say, well, my blockchain now is not the blocks themselves anymore, but just the hash value, because you can check whether if you have the old state and then see a new hash value, whether that was correctly derived, right? So what can you do? You can use some crypto magic. You can use a proof. A proof that the new hash value was correctly derived from the previous hash value, and do this in a very efficient way using a concept called SNARKs, which stands for succinct non-interactive arguments of knowledge. Never mind what this all stands for, but it's basically a way of proving any NP statement in a very efficient and short way. So what do I mean by an NP statement, or why is this what I want to show here, an NP statement? Well, if I give you my statement is, here's a hash value, here's a new hash value, then my width and my statement is this corresponds to, or this new hash value corresponds to a block that was legitimately obtained from the previous hash value, then that's an NP statement because there's a witness, namely this block. If I know the witness, I can efficiently check, is the new block, so the witness would be the two blocks. I can check whether the new block was correctly obtained from the previous one and whether these two blocks hash to these values. So what you could do is, instead of having the blocks and verifying their content, you just have these snapshots, these fingerprints, and the proofs that guarantee that things were done legitimately. That's already a very big space saving. So these SNARKs, they're only like kilobytes big, no matter how big the statement is that they prove. So how would your blockchain look like? So you start with your Genesis block. Every block gets hashed. So you have these hash values, and then you have proofs. And that would be your blockchain. Good, that's already amazing, but these people that invented Coda, they wanted to go further, because although this is very small, every block now has like a few kilobytes of additional data, so it would grow. So what they do is they say, well, if I have these proofs here that go from one hash of a block to the next one, I could just, again, using SNARKs to achieve constant size, have a proof that says there are proofs that go like from, and so there are proofs and intermediate hash values, and all of these proofs verify. And that's again an NP statement, so I can do a proof for it. So using these recursive SNARKs, what you can do is if you mine a new block, so this is your old system state, you have hash of the Genesis block, hash of the current block, proof that tells you everything was legit. You mine a new block, and now you can take an old proof, and from that and the fact that your new block follows from the previous block, make a new proof, which means that the size never grows. Good, that's it, and happy to take questions.
Wow. Thank you very much. Okay, there's a echo. Ah, it's better. Okay, no echo now. I have no idea why there was an echo. Good. Questions? Are there questions? At least there are enough people here. Of course, there's always the question of energy usage, no? And I guess the space efficient blockchains improve along this line. Nevertheless, it's still growing. Do you think this? Is there a certain point? I don't know. An end of this growing, or how does this continue?
I mean, this is kind of maps back to Krzysztof's talk, where the problem with Bitcoin, and Bitcoin still uses this concept of proof of work, is that to have this very stable way of achieving consensus, where people just keep computing hash values, and people buy ASICs hardware and warehouses full of them in the world, and electricity in the order of consumption of countries is used to maintain the system. That's really addressed by using proof of stake. So what Krzysztof talked about, you don't have consensus. So your chances of mining the next block and thus getting the reward is not proportional to how much electricity or computing power you invest, but how much money you have and how much you have staked. That's kind of the like quantum leap from crazy assumption to crazy consumption of electricity to something more sustainable. This talk was really about electricity, not electricity, but do we really need everyone to store this huge amount of blockchain data in order to have this security that comes from distributing the trust? I mean, yes, these SNARKs, they're also not so cheap to compute. And if you look at how this protocol actually works, this is kind of also outsourced to a different kind of miners. But if you look at what orders of magnitude it costs to compute the SNARK and what Bitcoin consumes, there's just no comparison.
I see. But we have now two questions. I start with Vincent. Perhaps you can ask your question, Vincent. Okay, disappeared. No, it's here.
Wait.
We can't hear. Wait. Okay, we wait.
Can you hear me now?
Now we can hear you.
Because I couldn't unmute myself. Okay, my question. You told us about that this protocol that you presented to us. Some bits, not for example Bitcoin and some other cryptocurrencies, adapted these schemes. How can a cryptocurrency like change its protocol that easy? Doesn't it invalidate all the transactions or all the computations that have been done before if you suddenly implement something new?
Ask Ethereum, they did that. No, that's actually why in Bitcoin this will probably never happen, because they're very conservative, and like even to do small modifications, it took a long time until they did this, and which was called, like they did a so-called soft fork, which would not invalidate earlier things, what happened before, because it's kind of compatible. Now, if you look at Monero, I think Monero also changed the system. Maybe Dominique knows more about this, because there's like more privacy methods that they added, and then they just redefine the protocol. So in Bitcoin, there's these proposals, and then there's kind of when these blocks are mined, you also signal whether you're okay with it or not. So then you get an idea of when like a quorum of the miners is okay with it, and then you just change the specification of the protocol. I mean, these things that I showed, like confidential transactions, that's something that I think for Monero that was there from the beginning on. But it's just a different cryptocurrency, so it's like independent of Bitcoin.
Dominic is raising his hand, so perhaps Dominic.
Hi, Georg, can you hear me?
Yes.
Yes.
Great talk. I really enjoyed it. So I wanted to go quickly back to the question about the energy consumption of SNARKs. So Zeta told me a few days ago that even computing SNARKs about, I think, a single block or so costs a few thousand US dollars. So I have no idea. Just out of curiosity, if this is true, if you have any experience there.
I mean, I would be surprised. I mean, I guess what she talks about is zk rollups, because that's her kind of related to her work. No, I don't have any numbers, but I would be a few $1,000s would surprise me. I know that the first system that used snarks in a large scale is probably Zcash, the first completely anonymous cryptocurrency. I mean, there the snarks are per transaction, but also there they improved a lot. In the beginning, it was like you had to, on a PC, compute for 2 minutes, and now it's, I think it's within seconds. Of course, the statement for Mina that you have to compute is bigger, but then I think, I mean, especially for this recursive snarks, because the statement is just that the new block was legitimately obtained from the previous block. So even if you express that as an like in these snark languages as an arithmetic circuit, I would be surprised if it's like, yeah, probably you have to compute for a day or so, but I don't think several $1,000s would surprise me. Maybe in Ethereum it's different, because there's just a lot more data, like of the whole blockchain data that's put into one snark. This recursive snarks, they avoid that, because you really only talk about just compared to, you have the proof for the old block, your statement is the transition to the new block and the validity of the old block, and that's kind of all you have to compute.
Thank you. Yeah, I know verification is super cheap of snarks. I'm just very curious. I would like to see real numbers.
Yeah,
thank you, Georg.
I don't. Maybe the Mina people tell you, but yeah, given that they have a market for computing snarks, it probably indicates that it's not something you can do in a few minutes on your laptop. But I don't think it's anyway like in case of badness anywhere near what Bitcoin does for consensus.
There is also in the direction of energy consumption another question. Are there any studies on the energy consumption at scale?
I mean, it's less. I mean, now what are we comparing, right? If you want to get rid of the Bitcoin energy consumption, then that's replacing the consensus mechanism. Now here, the approach was really, how can it's not so much about energy, it's about storage. Can I avoid like this blockchain data being stored in thousands of different nodes in the blockchain network. So then I guess it's different units that you compare, whether using a SNARKs costs energy, but you don't need space because you compressed everything.
Okay. Another question from Dominic.
Also, some studies claim that Bitcoin, or hear me double, that Bitcoin's energy comes already over 50% from renewable resources.
Yeah.
I don't know if this is true, but
I know the stories. And because some Bitcoin miner decided somewhere in Africa he wants to put a mining rig, that's why the local population also profited a lot because they have electricity now. You can do other things with energy.
Exactly. Professor Maffei also tries to convince me that everything very green. Okay.
He works exactly on not having all the data on the blockchain, but using different means by having these layer 2 protocols like Lightning.
Exactly. Look, are there any more questions? Since I don't see any in the chat, I really want to thank you, Georg. I didn't know that it's possible to be as energetic about this topic, but it was really very energetic. So you are behind it. I can really second Dominic. Great talk. Thank you very much.
Thanks for the invitation.
Yeah, we continue. Also there will be, I'm pretty sure we will have this next year again, since there are also now, 60 people online and there is more and more interest. And I think it's also more and more important that we as computer scientists consider this topic of sustainability in the sense of, energy consumption on different levels. Just a word about getting grades. As for those of you who are from TU Wien, it's in fact in a couple of minutes that you are able via Tuvel to select your topic about which you want to write a seminar paper. You have got all the information already before Christmas about that. There is also a slide deck explaining exactly how to write a paper, how to cite, and so on. If you have any questions, nevertheless, you can ask Marianne Schnellmann or myself by writing an email. If everything is clear, there's the timeline online. I think you have time now until end of February for the seminar paper. Then you have to review a paper of a peer, of a colleague, and I guess by something like mid-March, we have then finally also graded your work and you will get a certificate for the course. If there are any questions, you can write an email or also ask now, or stay a bit. I can stay a bit longer in the Zoom and you can just ask. So if there are no further comments, once again, Georg, thank you very much. Thank you also to all the participants for being kind of also enthusiastic about the topic. Yeah, and all the best and see you next time. Goodbye.
Bye-bye.